This is a video on the basic principles for determining latitude and longitude by the sun. We can look to the heavens to find our place here on Earth. In this video, we'll examine how our closest star, the sun, can be used to determine our position here on Earth. But of course, navigators and geographers also use the stars of the night sky to locate their position on Earth. And understanding how to determine our location by the most basic methods is valuable for several reasons. It provides a foundation for understanding modern methods like GPS. It provides a backup or a check should the GPS fail, for example, just if you had no batteries in your GPS device. And then we could also develop an understanding of the everyday motion of the sun through the sky and its relation to the seasons and the significance of the time zones. So lines of latitude increase as we travel north and south. The latitude is 0 at the equator and 90 degrees at the north and the south poles. Also, sometimes you'll have negative latitude for going south of the equator. Longitude increases as we travel east and west of the prime meridian. The location of the prime meridian, which is 0 degrees longitude, is really completely arbitrary, and the current 0-degree line was chosen in the 1800s. You'll also sometimes see negative degrees longitude when you travel to the west of 0, and positive degrees longitude as you travel to the east of 0. So the principles for finding latitude by the sun can be traced back to the ancient Greeks, who worked out the necessary geometry by about 200 BC. Finding longitude proved much more difficult. Through the Middle Ages and the Renaissance, sailors used dead reckoning to determine longitude. So trips across the Atlantic could be done by maintaining constant latitude and just continuing west or east. But with the age of exploration, the need for better navigation led to the invention of accurate clocks, which enabled an accurate determination of longitude. Other methods for determining longitude were found as well, for example, using the position of the moon, but this required much more complex mathematics and it could take hours to complete. So Eratosthenes, he lived from 276 to 194 BCE. He was one of the first to develop and use the idea of latitude and longitude. This is a picture of a map that is Eratosthenes' map of the world that he knew. You can see the vertical and horizontal lines for latitude and longitude. Now, Eratosthenes knew that the Earth was a sphere, and he made a very accurate estimate for the size of the entire Earth as a sphere. But the map shown here is just the land boundaries that he knew about at the time, with the vertical and horizontal lines for latitude and longitude drawn in. And over 1,000 years ago, Viking sailors determined their latitude by watching the sun. A sundial could be kept floating in a bowl to keep it level, and a circle on the board in that bowl could indicate a line the shadow would reach if the ship was on the desired latitude. So to find latitude, we must find the angle of elevation of the sun, and we must also know the season, as this angle changes with the seasons. To have a convenient common reference point, we will measure the angle of elevation of the sun at the local noon time when it reaches its highest point in the sky. So let's call this angle E. In ancient times, this angle could be found with an astrolabe. The cross staff, shown in this 17th century navigation journal, could measure an angle of elevation of the sun as well, but didn't work well at sea. On a rolling ship, either you would blind yourself looking at the sun, or you'd poke your eye out as the ship rolled on the waves. So the backstaff developed around the 1600s, and some variations are shown in the pictures here. Thomas Godfrey, who lived from 1704 to 1749, was an optician and inventor in Philadelphia who invented the octant around 1730. At approximately the same time, an Englishman, John Hadley, also invented the octant independently. Below is a diagram from an article by Hadley. And the octant was a precursor to the sextant. The sextant was developed in the 1700s, and it's still used today as a backup to the GPS navigation because the sextant doesn't require electricity or batteries. Now we also have to know the sun's declination, which depends on the season, and it's a result of the tilt of the Earth's axis of rotation. We include this declination when we're finding our latitude. So in the northern hemisphere, the declination changes from 23.5 degrees in the summer, when the Earth is tilted toward the sun, to negative 23.5 in the winter when the Earth is tilted away from the sun. And the declination is 0 degrees at the spring and autumnal equinox. You can see a list here of the declination as it changes through the year. These declinations are valid no matter where you are on the globe. It's the same value. You'll experience warm temperatures in June in the northern hemisphere and colder temperatures in June in the southern hemisphere. But the declination is the same anywhere on the globe. So the declination is related to the seasons. The sun passes directly above the equator at each equinox when you have 0 degrees declination. It passes directly above the Tropic of Cancer in June when you're at 23.5 degrees declination, and the sun passes above the Tropic of Capricorn in December, which is negative 23.5 degrees declination. Well, in spring or fall, when the sun is directly above the equator, the sun's declination is at 0. At that time, the latitude is simply the complement of the angle of elevation of the sun. You see in the diagram here I have theta is the latitude. It's an angle that's measured from 0 degrees horizontal. And that angle theta is the same as the complement of the angle of elevation. You see the E there is the angle of elevation. It's the angle measured to the sun. This line of latitude is straight from the center of the Earth going straight up vertical at whatever point you're standing at. So if you measured the angle of elevation to the sun, the complement of that angle is theta. So we know that theta plus E is 90 degrees, and therefore we could write theta as 90 degrees minus whatever the angle of elevation is. So measure the angle of elevation of the sun, subtract it from 90, and that's the latitude. That's only true in approximately March and September when the declination is 0. Other times during the year, the North Pole is tilted away or toward the sun. For example, in the summer in the northern hemisphere, the North Pole is tilted toward the sun. So you see here in the diagram I have theta is again the angle of latitude. Here's D, this is the sun's declination. In this case it's a positive number. And you notice how theta subtract D is this angle up here, the complement of E. So E plus theta minus D makes 90 degrees as before. So solving for theta, I have the angle of latitude is 90 degrees minus the elevation plus the sun's declination. Now this is a diagram that still has the North Pole tilted toward the sun and therefore a positive declination. D is positive in this diagram. But let's say you wanted to find your latitude and you were in the southern hemisphere. You notice how this angle theta, which is the latitude measured from the equator, theta plus D, which is the sun's declination, together makes this complement of the angle E. And therefore the angle E plus theta plus D all together makes 90 degrees. The angle of elevation plus theta plus D all together makes 90 degrees, and therefore the angle of latitude theta is 90 degrees minus the angle of elevation minus the declination. So these formulas are valid for any time of the year. as the North Pole is tilting toward and also away from the sun, and when it's neither tilted away nor toward. And however, if you're in the northern hemisphere, you have to add this declination. If you're in the southern hemisphere, you have to subtract it. So we have two formulas. Pay attention to whether you're in the northern or southern hemisphere when you're doing these calculations to find your latitude. Okay, so an example. In January, in Philadelphia, we'd measure the angle of elevation of the sun at noon to be about 30 degrees. That's the highest it gets into the sky at noon, or that's as high as it gets all day, about 30 degrees in January. And at that time, the sun's declination in January all over the world is about negative 20 degrees. So what's the latitude for Philadelphia? Well, I'm in the northern hemisphere, so I have the plus d. 90 minus the angle of elevation plus the declination. That's 90 minus the 30 degree angle of elevation plus that negative 20 degree declination. 90 minus 30 plus negative 20 all comes out 40 degrees. So we say that's 40 degrees latitude or 40 degrees north latitude. Another example, in Miami in September. The angle of elevation of the sun at noon is about 65 degrees, so it reaches a height of 65 degrees at noon, the sun does, and in September you're close to the autumnal equinox, so you're pretty close to zero declination. So if you take zero declination, what is Miami's latitude? So the same formula, northern hemisphere, 90 minus angle of elevation plus declination, that's 90 minus 65, the angle of elevation, plus 0, the declination. 90 minus 65 gives me 25 degrees latitude for Miami. So now let's look at longitude. The equator is the intersection of the surface of the Earth with a plane that is perpendicular to the Earth's axis of rotation. So as a result, there's a natural choice for 0 degrees latitude. But there's really no natural choice for where to put 0 longitude. That's what's called the prime meridian. And historically, there have been many different choices for that location of 0 degrees longitude. Depending on what country you live in, you might use a different, more convenient 0 degree longitude. So currently, throughout the world, we use a line running through Greenwich, England, which is close to London, for the north to south, through England from the north to the south as our prime meridian. So finding latitude has been relatively easy since ancient times. You only have to know the date and the angle of elevation of the sun. But historically, finding longitude was a much more challenging problem. But as travel across the ocean became more important in the 1600s and 1700s, the challenge of finding longitude became more important. Many sailors lost their lives due to the difficulty in finding longitude. Over 1,000 British soldiers died as a result of an error in navigation. In one incident in 1707, a famous incident, the British government, as a result, created the Longitude Prize in 1714 to be awarded to anyone that could solve the problem of finding longitude. This is a picture from a naval disaster in 1741. So the Longitude Prize was worth about or over $4 million in today's dollars. And it was to be paid by the British government to anyone that could solve the problem of finding longitude, particularly at sea. And John Harrison, who lived from 1693 to 1776, won the prize. He actually won most of the prize money, didn't actually officially win the prize. They were pretty picky about the details, but he was given many, many grants to continue working on it. And if you looked at all the money that he got from them, it was most of the prize money. He invented a very accurate clock that could be used at sea, and he solved the problem of finding longitude. That's essentially the foundation for how it's done today. Harrison's solution to the problem of finding longitude was, you set a clock A, to the current time at your starting point, and you take that clock with you on your trip. You compare the local time with the time on clock A. And each hour of difference between the local time and clock A is 15 degrees of longitude. If If we travel west, local time is behind clock A. If we travel to the east, local time is ahead of clock A. This is the reason we have time zones. Each time zone is 15 degrees of longitude, and there are 24 time zones around the Earth. Note that 15 times 24 is 360 degrees for one rotation around the Earth. So as an example, suppose clock A is set to the time in London, England. And when local noon arrives, we're somewhere else at our current location. At clock A says the time is 11 a.m. and we see local noon because we see the sun reach its highest angle of elevation. So that's a local noon. So what is our longitude? Our local time is exactly an hour ahead of London. Since London is at 0 degrees longitude, we are at 15 degrees longitude, and we're to the east of London because our noon is occurring before London. So sometimes we use positive longitude when we're east of London and negative longitude when you're west of London. Example 2. Clock A is set to the time in London, which is also referred to as Greenwich Mean Time. At local noon, suppose we observe that clock A reads 2:30 p.m. So what's our longitude? The difference in time here is 2 hours and 30 minutes, and we're behind London. That's 2 hours. 2 hours is 30 degrees because each hour is 15 degrees. So 2 hours times 15 degrees per hour, that's 30 degrees. And that 30 minutes at 15 degrees per hour is, let's say 30 minutes is 0.5 hours. So 0.5 times 15 gives me 7.5 degrees. So our longitude is about 37.5 degrees west of London. 35 degrees west, or negative 37.5 degrees. Example 3. Suppose local noon occurs when a clock set to Greenwich London time displays 4:17 a.m. So what's our longitude? So in this example, we're ahead of Greenwich by 7 hours and 43 minutes. Right? 43 minutes would put me at 5 a.m. and then another 7 hours makes noon. But local noon is occurring before London, 7 hours and 43 minutes before. So we're to the east of London. Each hour is 15 degrees of longitude, so 60 minutes is 15 degrees of longitude. Divide both of those by 15 and you realize that every 4 minutes is 1 degree of longitude. If you divide both of those by 4, you see that 1 minute is 1/4 of a degree in longitude. So the 7 hours difference at 15 degrees every hour, 75 degrees, and those 43 minutes at 1/4 of a degree per minute is 10 degrees, 10.75 degrees. So since we're 7 hours and 43 minutes ahead, local noon occurring before London noon, we could say that if you add those two together, 75 plus the 10.75, you have 85.75 degrees longitude east. So example 4. Captain James Cook has reached land on June 8th. When the sun's declination is about 22.9 degrees. So Captain Cook would be looking up at a table, maybe the paper that you see there in the picture. It looks like maybe a map, but he would look up the time of the year and what the sun's declination is, and let's say he was sailing west from England and he measures the position of the sun and he finds the following information. At local noon, the sun reaches an angle of elevation of 75.6 degrees. And the time on the ship's navigational clock indicates the time in London, England is 5:06 p.m. So what's the latitude and longitude for Captain Cook? So let me challenge you to pause the video right there, see if you can figure this out based on those previous examples. Work it out, and then restart the video and see if you got the right answer. First, let's do Cook's latitude. Latitude in the northern hemisphere is 90 degrees minus the angle of elevation plus the declination. He could know that he was in the northern hemisphere because it's June and it's warm. So you do 90 minus the 75.6 degrees angle of elevation plus the 22.9 degrees declination, and you have 37.3 degrees north latitude. And the longitude, looking at the difference between noon local and 5:06 p.m. in London, means that noon has already passed in London, It's already 5:06 p.m., so we're kind of behind here, having local noon occurring sort of after it's already occurred in London by 5 hours and 6 minutes. So 5 hours times 15 degrees an hour is 75 degrees, and those 6 minutes at quarter of a degree every minute is 1.75 degrees. Add those two together, and the fact that we're behind London, local noon is after London's noon. Our longitude is 76.7 degrees west, or negative 76.75 degrees. Well, that conclusion, latitude 37.3 degrees north and longitude 76.75 degrees west, is pretty close to Williamsburg, Virginia. Okay, that's the end of the video. Thank you for watching. Some recommended reading is Longitude, the true story of a lone genius who solved the greatest scientific problem of his time, by Dava Sobel. And that's the story of John Harrison and the method of finding longitude by looking at time. Another movie that's really good is this Longitude in the year 2000 with Jeremy Irons and Michael Gambon. It's also the story of John Harrison and his clock.